The second half of the post-lunch session today is a talk by Fernando Reyes Lega from Colombia. He will be talking on quantum field theory and quantum space-time.
Well, thank you, Viswajit. Well, let me start by thanking the organizers for this conference, which I have enjoyed a lot. So there is trip that we did like 7 years ago, I think, in 2015, with Val to the desert of Tatacoa. And during that time, we were discussing some problems with entropy ambiguities, and we were discussing POVMs. Then during that time, we also discussed some entropy problems. And Val suggested using a version of geometric phases that is designed to work for density matrices. So I decided to talk about this work because it is just an instance that makes it clear how far Val's influence has been in my research work. Namely, Val insisted on using this type of structures. Well, at the time, we were looking for some kind of second law of thermodynamics in quantum systems. I mean, that project is kind of dormant, but I found another application in this other setting, and this is one of the reasons I want to present this. And that allows me also to express my deep gratitude to Val for his generosity all these years. Well, now I should also mention that this work has been done in collaboration with two of my students, Sobat Taban and Lin Sequeira, and a postdoc in our group, Javier Asa. Well, let me start with a motivation for this work, which I have decided to put in this kind of picture. So what you see on the left side is a typical diagram. Typical diagram where we might have a quantum critical point here, a quantum phase transition taking place at 0 temperature. And there is also the possibility that there is thermal phase transition. It does not happen for all systems, but this might happen. And for purely quantum phase transitions, there is a transition regime called the quantum critical region. Now, my interest in this type of structures started when I wanted to give a kind of topological characterization of certain quantum critical points. At the time I started looking at these problems, well, that was around 2008. Then the whole story about topological insulators and their topological characterizations started. So somehow I got involved in that also, but my main motivation came from just studying this possibility of describing, using some topological tools, what happens when we have quantum phase transitions. Now, when you look at the periodic table of topological insulators and superconductors, you realize, well, there are different versions, different ways to come to this periodic table. But in the end, there is more or less an agreement that there are certain symmetries that has to be taken into account of time reversal type or chirality. And there is periodicity which is, I mean, for which the Bott periodicity somehow lies behind. And there is the possibility of expressing the different types of invariance that we have there in terms of K-theory. Now, for some of these classes, it is also possible to construct a kind of pairing which gives the topological invariance as indexes. But that is not the case for all classes. So if we take the simplest class, which is the D class, for which we only have particle-hole symmetry, it is not that easy to come up with a formula which we can compute, no? Because we can think of it as a kind of system which has torsion, speaking in geometric terms. Now, important examples as the classical Ising model in 2 dimensions, which is a classical model, can be characterized in topological terms, basically because we have the classical quantum map, and I mean, we can use the transfer matrix to construct a classical quantum map. So we can map that model to a spin chain model. This spin chain model can be mapped to a fermion model. So it is so that Araki, Evans, and other people constructed a type of index, which is C2 valued. That was during the 80s. And they were able to characterize this thermal phase transition of the Ising model in terms of that type of index. But this is not an index that you can compute through a local formula. It is something different. And well, as there is a mathematical equivalence between the Ising spin chain and the Kitaev model, or the XY model also, it is just a matter of reinterpreting the values of the meaning of the parameters in the Hamiltonian. It turns out that this index is also related to the appearance of edge modes in the Kitaev model, in the one-dimensional one. Now, my interest here is mainly centered around 2 aspects. First of all, starting with only this index, which is a very coarse type of invariant, we are interested in the question of, well, can we generalize this type of invariant to systems with interaction, I mean, the interaction among fermions? And secondly, what happens if we include temperature? So as you see in this diagram, for instance, if I focus on the Ising model, then we know in the Ising spin chain or the XY chain, we know that there is a quantum phase transition taking place in terms of the magnetic field here. And there is a topological invariant, this C2 index, which characterizes the phase transition. But the question then arises whether it is possible to also give a topological characterization of what happens at higher temperatures. So this is our second motivation, and I will focus on that second motivation in the second part of the talk. Okay, so I will describe a first work we did, which is of a more formal character. One could ask why bother with all these formalities, but the point is that the formalism we are using here is quite well suited to study the interacting problem, which is a problem we are starting to work on. So let me give a few definitions. So first I will define what is called a self-dual Kerr algebra. This is just a way of describing fermionic systems. We have canonical commutation relations, but these are not the usual creation and annihilation operators. Namely, this is not the Kerr algebra. We have real structure conjugation, which allows us to somehow include both creation and annihilation operators in a single term, which is called B. No? So we have a Hilbert space. Out of this Hilbert space, together with the conjugation, we construct this type of algebra, which can be shown to give equivalent results as the Kerr algebra or the Clifford algebra. This type of algebra was used, was developed and used by Araki during the 80s. And it is quite useful if we are interested in Hamiltonians of quadratic type, so of the mean field type, which are the relevant ones if we are interested in topological insulators and superconductors without interactions. Now, the point that we don't have an a priori choice of vacuum state before we diagonalize a given Hamiltonian is captured here in the following way. Instead of considering an initial vacuum, we can consider all of them at the same time. So what we do is we pick a projection on the one particle Hilbert space, and we move these projections until we are able to diagonalize the Hamiltonian. So what Araki did was to show that it is always possible to find such projections, and they are called basis projections. They are projections on Hilbert space which satisfy this property, which is called the self-dual property. Once you have a self-dual projection, then you can show that the Hilbert space will split in this form, which is what we also find in the literature as the Nambu space. So the formalism is just a bit more mathematical version of Nambu's Nambu space. And this leads, in turn, to the composition of these operators in creation and annihilation parts. Well, Bogoliubov transformations in this context are given by unitaries that commute with the real structure, and they induce automorphisms, no, in this way. No? So you can work on generators, and the transformed generator is given by this expression. Now, if 1 minus u is of trace class, then you can compute the determinant, and one can show that this determinant has to be plus or minus 1. What is the meaning of this plus or minus 1? Well, this is a way of classifying possible ground states according to their parity. No? So this is where the C2 index will come from. So somehow you can think of having the space of possible ground states in this context of Majorana type, and you will have two connected components. If you add more symmetries, like for instance U1 symmetry, then this space of ground states will decompose in charge sectors and so on. Now, Hamiltonians can be described as elements of the algebra in terms of so-called bilinear elements, and these are quadratic elements in the algebra of this type. So you need, well, here we assume that the one particle Hamiltonian is a bounded operator, and you use that in order to define these quadratic forms. So they have adjoints of this type, well, then we are interested in diagonalizing these operators, and in the context of topological materials, what we have are families of such Hamiltonians, and we are interested in describing phases of matter in terms of sectors defined by the closing of the gap. No? So if we are able to keep the gap open while preserving the symmetries, we will define this to be a phase of matter. And typically what happens is that if the gap is closed, then we have changed a phase. Self-dual Hamiltonians are Hamiltonians which satisfy this property. They change sign under conjugation by gamma. And we say that a basis projection diagonalizes the Hamiltonian if it satisfies this property. So this is basically, if we find such a basis projection, we are done with the diagonalization problem, and one can show that such a projection always exists. We can define dynamics in a similar fashion, no? And the interesting point is that since the type of Hamiltonians is quite simple, the dynamics of the many particle space will be determined by the dynamics in the one particle or the initial Hilbert space. Now, coming to the definition of states, the space of states is, of course, quite a complicated space, but we can restrict to the class of so-called quasi-free states, which are basically states of vacuum, of free theory type. No? So they obey Wick's theorem. So basically, once we have the two-point function, we can compute all other correlation functions. And there is a way of characterizing these two-point functions in terms of so-called symbols, which are operators obeying these two properties. So the two-point function of such a state is given by the inner product of the two vectors phi1 and phi2 in this case, where we introduce here the operator S. Now, this operator S will be important for me because in case we have a ground state which is a pure state, we can use a projection which is computed out of the Hamiltonian for S. But in the case of thermal states, we can also define an operator S, which gives us the corresponding KMS states. And the geometric phases we are going to talk about are computed out of this type of operators in the thermal case. In this context, when we have an algebraic description of the Kerr or the self-dual Kerr algebra, a ground state is defined in terms of the dynamics. No? So the dynamics is given by a family of automorphisms. If we take the time derivative of this family, of this one parameter group of automorphisms, we get something which is called a derivation, no? In the algebra. And for elements that belong to the domain of this derivation, we can characterize a ground state omega as a state fulfilling this property. No? This is equivalent to saying that the ground state is the lowest energy state, so somehow. Okay, once we have this, we can now use the spectral decomposition of the Hamiltonian, and if we have a gap, we will have a projector to the vanishing part of the spectrum, and we will have projections to the positive and negative part of the spectrum. Now, if our Hamiltonian is gapped, then because of this property that this follows basically because the Hamiltonian is a self-dual Hamiltonian, then these projections will become basis projections. So this is how we can diagonalize the Hamiltonian. Okay, now I will just make a couple of assumptions. I want to work with families of Hamiltonians. So let us assume that I have, in the space of self-dual Hamiltonians, I consider a path. No? So I have a Hamiltonian H0, H1, let's say, and I am going along this path. So I have a family of Hamiltonians HS. Assuming certain differentiability properties of these Hamiltonians, then we can prove the following. If along the path the gap is opened, so having gap along this path would mean that we are connecting two Hamiltonians that belong to the same phase. Here, in this simple case, we are not including other symmetries, so this is a very simple setting. So the idea is to show that we can define an index following Araki, which does not change along the path. So a change in the index would mean that the gap has been closed and we have changed phase. Now, how is the index defined? Well, if we have two Hamiltonians, and if they are gapped, then the ground state will be unique, and we can associate basis projections to the ground states. Now, if the difference between these two projections is of Hilbert-Schmidt type, we can project, take the range of these projections, take their intersection, and compute its dimension. It will be finite dimensional because the difference between P1 and P2 will be Hilbert-Schmidt. Now, according to the evenness or oddness of the dimension of this space, we will get the possible values of this index. No? So it can be shown that this index is a topological index. It is continuous. And this is a general way of, if we go to a concrete example like the Kitaev model, this coincides with the C2 index defined by Kitaev in terms of Paphians. So one theorem we have worked out says basically the following. So we have this family for which we assume we can take derivatives. So we can compute the derivative of HS with respect to the parameter. And we assume that the gap is kept open along the path. So we want to prove that the index will not change, but we also want to prove that we can connect any two Hamiltonians by means of a unitary map, actually a unitary that connects the corresponding basis projections. No? So first, this is the unitary equivalence. It is given by a family of unitaries V, which satisfy a certain differential equation, which is this one. No? So this is interesting for us because if you see, let E plus be the projection to the positive part of the spectrum. This is a projector, and this type of differential equation is, I mean, it resembles what we have when we discuss Berry's phases, no? So like a parallel transport equation. And this is what we are going to use in order to try to find some kind of topological description in the thermal case. Now, it is also possible to show that these automorphisms induced by the unitaries V's are inner. This is basically something that we obtain through the fact that 1 minus V is trace class. So the difficulty here in the thermodynamic limit is in showing that 1 minus V is of trace class. So this is, I mean, there are certain bounds that can be worked out, and this can be shown. And then, well, one shows that along the path, the index that we assign to any two Hamiltonians along this path remains invariant. I will, because I want to focus on the thermal part, I will skip these details. They are in this reference, so we can discuss them for whoever wants. And there is also another theorem that we worked, which is a slight modification of a theorem by Araki. And it is interesting because from the first theorem, it follows that if along a path of a continuous path of Hamiltonians, there is a change in the index, then the gap must close. So one would like to know what happens with the points where the gap closes. For instance, in the case of the XY chain, at the critical point, there are precisely two pure states which are not invariant under the C2 symmetry of the XY model, but they are pure and they transform into each other. But they are not the only ground states, so you can take any mixture of those states, and this gives a more big family. Now, this theorem is interesting because the degeneracy space somehow gives a lot of freedom to modify the ground state, so you will have a big family of ground states at the point where the gap closes. No? So this theorem basically gives a characterization of the possibilities you have for the ground state. Okay, so far with this formalism, so as said, this looks like a lot of luggage to carry, no? Just to study simple models. But the motivation is that in the interacting case, there are tools coming from this field of mathematical physics, which could be useful in order to find a way of defining topological invariance in the interacting case, which is quite an open problem. So I will skip that, and I will now focus on more concrete situations. So let me recall the XY chain, no, as a spin chain, which can be written just by using the Wigner-Jordan transformation as a fermionic problem. This can be mapped to the self-dual Kerr algebra, and it can be worked out directly in the thermodynamic limit. But here I will focus on finite systems. So this is a more physical way of treating the problem. So in this case, as you know, there is a critical point when lambda, well, there are several critical regions, but the one we are interested in is the one that occurs when gamma is different from 0, and lambda is equal to 1. So at lambda equal to 1, we have a critical point, and there is an order parameter. But here, at 0 temperature, the longitudinal magnetization, well, it has to be computed carefully because the C2 symmetry would make it vanish a priori. So one has to be careful in defining this magnetization. But the point is that it can be computed analytically. I mean, this looks simple here, but when you try to do it numerically, you are confronted with the fact that you have to compute the determinant of matrices that grow very large. No? So numerically, this is a kind of problem where Cn are given by this term. So this is the magnetization now depending on the temperature. Now, in this case, we will have a diagram which is very much like the one I was drawing. So here we have the magnetic field, here temperature. There is a C2 invariant which tells us whether we are in this region or in this region. But here there is, I mean, since there is no thermal phase transition in this model, well, we don't know what happens. Now, some team of Spanish physicists, so Villuela and Martin Martinez, they did compute a Berry phase in momentum space that produces a figure very much like that one. What we did was to compute this longitudinal magnetization and show that it coincides with what this Berry phase is doing. No? Now, but Berry phase is not completely of topological character. It depends on the path that we choose. No? So here, below, we have a topological invariant describing the change of phase. Here, there is not really a change of phase, but there is a change of regime between ferromagnetic and paramagnetic. But nevertheless, when one computes the Berry phase in momentum space, at 0 temperature, one recovers exactly the C2 value, or the value of the C2 invariant. And here, we still get a holonomy for the Berry phase, for the Berry connection, which is either plus or minus 1. So this is intriguing, no? That the Berry phase takes precisely these values, and we are looking for a way of understanding this in more topological terms, possibly in the context of the self-dual algebra. Now, this kind of systems this is not actually a one-dimensional system which can be modeled exactly with the XY chain, but more or less shows the type of behavior that I am displaying here. Now, if we go now to the Kitaev chain, well, this is well known, no? That we have a topological regime where we have edge states and another one where we don't have edge states. So with one student of mine, Juan Calderon, we studied finite versions of the Kitaev chain, and we computed this type of C2 index in the finite dimensional case. By the properties of this index, it is possible to define it in the finite dimensional case because it is not the index of an operator in the usual way of a Fredholm. I mean, its Fredholm index is 0, even in the infinite dimensional case. But the dimension of the kernel is finite, given that it is a Fredholm operator, and the index is defined through its dimension. So you can compute it in the finite dimensional case. And you see, when we use periodic boundary conditions, when we start enlarging the system, we get something that resembles this kind of light cone in the Kitaev model. But with open boundary conditions, we can still compute the invariant, but it doesn't have a meaning in terms of edge states. No? Okay, now talking about edge states in the Kitaev chain. There are several ways of trying to characterize the presence of edge states. Some of them are better, I mean, they show the features better than others, but I will focus on the following one. So if I take the initial Fermi operators and separate them in terms of Majorana fermions, gamma A and gamma B, then after we have performed the corresponding Bogoliubov transformation, then the coefficients in the finite case can be regarded as the wave functions of the Majorana fermions. So this can be plotted. So for instance, in a region which is non-topological for a chain of 60 sites, you have this distribution of the Majorana fermions. But if we go to the topological regime, even at a small number of sites like 60, you see how the edge modes start to move to the edges. No? So the red to the right-hand side and the blue to the left-hand side. So apart from describing the change in magnetization in the XY model, we are interested in describing edge modes in the Kitaev model. Now, you would say, but come on, the Kitaev model is just it's just the same XY model with another interpretation. Now, the point is that the Berry phase or Ullmann phase that has been computed in the case of the XY model, well, we have shown that it coincides precisely with the plot that we get for the change of regime in magnetization, in longitudinal magnetization. But for edge states, it has been claimed that there is no direct resemblance to Ullmann's phase. And this is what we want to understand. No? So what is happening there? So,
Andres,
yes.
10 minutes left.
Thank you. So if I now start introducing temperature, so now I just keep the left-hand side, so the Majorana fermions on the left edge, but I start adding temperature. So red color means there is temperature, and blue means it is zero temperature. So you see, as we start increasing the temperature, then these edge states start to melt, so to say. No? So if the temperature is too high, all modes will be equally occupied, and the edge states have disappeared. So, question, is it possible to give a topological characterization of what is going on here? Well, this is what we have been exploring. And for this, we have used generalization of Berry's phase, which is suitable to treat density matrices. But we have not done it with density matrices. We have done it with the symbols S that define thermal states. No? So these symbols are operators on the one-particle Hilbert space. They are positive operators, and the same formalism that Ullmann, Dabrowski, and Grosse, and others used many years ago to define geometric phases for density matrices can be used in this context. So just to give a quick overview of how this construction goes, the idea is we want to define a generalization of Berry's phase for density matrices. So you start by decomposing a density matrix in terms of its spectral projection. Then a purification can be constructed in this way, no? Using a basis for coming from the spectral decomposition. But there is an ambiguity here. You can add a unitary operator acting on the right-hand side, and you will get the same density matrix. So this defines a bundle-like structure in the space of Hilbert-Schmidt operators. I mean, I am using this isomorphism between Hilbert-Schmidt operators and the tensor product of H with itself in the real case. So we get a kind of bundle structure, and then if we use the Hilbert-Schmidt inner product, only its real part, its symmetric part, in order to define the notion of horizontal space, we will get a connection, and then we will be able to talk about horizontal lifts of paths of density matrices. The nice feature of this construction is that when you go to zero temperature, you recover Berry's phase. So it is a nice generalization of what we call Berry phase. There are many other possibilities for connections, and we have been exploring some of them, but so far the one that works better is this one. So we have vertical spaces just given by the fact that we can map Hilbert-Schmidt operators to density matrices, and then using the symmetric part of the inner product, we can define the notion of horizontal space, as shown in equation 23, and then it all boils down to solving these differential equations. No? So A is a lift, A of t is a lift of a path rho of t, where rho is a positive operator. And the solution is given once you can show that this operator t is given by this expression down here, and everything boils down to solving this equation. Now, if we do it for the XY model, then what we get is the following. So this holonomy we are integrating in momentum space. It will give only two values, plus or minus 1, and these are the two colors pointed here. So this computation was done by Villuela and Martin Martinez, but what we did was to compute numerically the longitudinal magnetization and to show that it is very close to, if we were able to improve our numerics, you would see that it coincides with this Ullmann's phase computation. so here you can see more or less what is going on. So for chains of different sizes, it gets better and better. So the change in Ullmann's phase is given at the value 1. And the magnetization actually starts going down to 0 as we increase the number of sites in the chain. Now, a three-dimensional plot of what is going on here. So you see that near the critical point, we still have some problems. This is still an ongoing project, but this should be no problem if we can improve the numerics. Now, the other computation we have been doing is using this computation of edge states in the thermal case, as I showed you before. Well, there is no abrupt transition between a regime that supports edge states. I mean, I am changing the temperature, no? So let us assume we are sitting in a point on parameter space which supports edge modes at 0 temperature. So we have well-defined edge modes. I start raising the temperature, and these edge modes, you can tell, okay, they still resemble the original edge modes, but at some point you say they are not there anymore. There is no abrupt transition. So I have plotted this change of behavior in a more or less graphic way. It looks like this. So what I do is the following. If at 0 temperature, the edge modes behave somewhat like this for a finite chain, and if I increase the temperature, it will behave like this. So I compare the value at the middle of the chain with the maximum value that it takes, which is at the edge. So this gives us a qualitative picture of what is going on, and the picture the plot that you get is like this. Now, if you compare it with the computation of the Ullmann phase, you will get this one. Now, well, this is as far as we have gotten, but there is something which is even more interesting for me, which is that the computations we have done have been done not with the density matrix itself, but with this operator. And this operator can be, I mean, this in case of thermal states, that operator depends on the temperature, and we can lift this operator to a projection, to a self-dual projection, which means this is something analogous to thermofield dynamics. So instead of working with the KMS state, we work with a pure state in an amplified Hilbert space, and there we have a projection. Now, what does it mean to have a projection? So in principle, if the system would allow us to compute the invariant using, for instance, cyclic cohomology, which is not the case here, but in such cases where it is possible, one could use that projection in order to compute an index. For the systems we have worked out, well, this will not work because it does not work at 0 temperature. But what does happen is that since we have a projection, we can now compute the usual Berry phase related to that projector. And what we have shown is that it coincides with the Ullmann phase computed for the symbol. So what I am trying to say is that this theory of Ullmann phase, so quantum holonomy for mixed states, can be modified so that you start with the density matrix, you purify the state. Up there in this bigger Hilbert space, you can compute a usual Berry phase, and then the holonomy of these two will coincide. We have checked that in a few examples, and it seems to work, and we are working on a general version of that. Now, so the remaining goal is then, and with this I will finish, remains in trying to see if it is possible to come up with a topological characterization of this transition regime. I mean, so far it is given by a geometric property of the Ullmann phase, but it would be very nice if we could come up with a topological characterization, perhaps related to K-theory in other instances. So, well, with this I will end, and I would like to wish Val a very happy birthday. Thank you very much.
Thank you for a wonderful talk and the felicitations. I enjoyed my trips to Bogota enormously, especially that money when
El Mani, of course.
when you were eating. Very good. We miss it here. So thank you again and very nice talk. There will be questions, I think.
Hi, Andres.
Hi.
Thanks for the nice talk. I have a question. See, as you know, let's say you take a long-range Kitaev chain, right? So you could look at the quantum phase transitions by looking at the behavior of entanglement entropy
Yes.
or circuit complexity and things like that. So would this classification that you are proposing be somehow related to the classifications that come from those physical parameters?
Well, in the case of the kit, or let me talk about the XY chain, but it's the same. No?
Yeah.
So we know that at the critical point in the low energy regime, we can get a conformal field theory, and we know what the central charge is, and the behavior of the entropy will give this log behavior. No? So this is a way of characterizing the quantum phase transition, but this is happening at zero temperature. No? Now, what this type of C2 index does, and this is what Kitaev proposed many years ago, is to use, still at zero temperature, a topological index that changes precisely when you cross the critical point. No? Yes. Now, to my surprise, when I started studying these topics, I found out that Araki had already done that, I mean, many years before Kitaev, with the classical Ising model by means of the transfer matrix method. And he had already defined this type of index I am using. So what you can do is you can show that this weird definition of the index in terms of projections boils down to Kitaev's definition in terms of Apfafia. No? Now, our motivation is a bit different. If I go back to this diagram, let's say this is the Kitaev chain, then at zero temperature, here we have this log behavior of the entanglement entropy. Here, entropy to the left and to the right will saturate. No? So this gives us a hint about the phase transition. And we have a topological index here on this side and on this side. But there is no topological index so far that has been defined which tell us about the behavior that we have on this when temperature is greater than zero. In the case of the Kitaev chain, well, it is not clear. I mean, I showed you pictures now for finite chains that when we start increasing the temperature, edge states will eventually fade away, but this transition is not abrupt. No? So, well, the question remains, how can we describe this transition? In any case, there is some sort of transition. No? Now, in other models, like for instance, the Su-Schrieffer-Heger model, where you actually can use cyclic cohomology to compute the invariant, we have the hope that it will be possible to define an invariant even in the temperature case. I mean, this is still something we have to try. No? But
right, in the SSH model, let's say at zero temperature, the circuit complexity also indicates the different phases.
Yes,
so
yes.
I was wondering, SSH is a good model, so would it correspond to this C2 classification?
Yes. Yeah, somehow we are trying to characterize in topological terms in the same way that it has been done for topological insulators, certain other features of these models. No?
Okay, thanks.
So if I understood correctly, you needed a gap for most of this. Do you have any idea what would happen if you've got an extended critical phase where you've got a gapless phase with that you can change parameters?
Yes, that part I skipped, no?
Oh, okay.
But you give me the chance to go back to that. So, for instance, as I was saying in the Ising chain model or XY chain model, the critical point will give you two different ground states which are pure. they are each one mapped to each other by the action of the C2 symmetry group you have in that case. But that doesn't mean that you only have two ground states. You can come up with any combination of those as a mixed state, and it will still be a ground state. So this result is actually, I mean, this theorem is a slight modification of something that Araki did. So I can try to describe it in a few words as follows. If there is gap, then we can decompose the Hilbert space in a part which contains the zero modes, so to say, and a part which does not. So let us call K0 the part that contains the zero modes. That means that the algebra of fermionic operators will factorize in this way, so accordingly. So now we define two subalgebras, A1 and A2, A0, and what can be done is as follows. If you consider elements of the algebra, since it is a factorized algebra, you can take elements A1 in big A1 and A0, and any ground state has to have this form. So what you do is you quotient out the zero modes, and in that case you can still have a self-dual projection P tilde. Now, there is a remaining part here, and there is a lot of freedom, because what can be shown is that you can choose any state you like in the algebra corresponding to the zero modes. This will still be a ground state. That's a general result that was obtained by Araki. No? I mean, it is intriguing for us. What we were interested in was in following, assuming the gap closes only at one point, following a path that closes at one point. Now, if the gap is open, the ground state is unique, and you have a well-defined basis projection. So you can also induce a path of projections, and they will go, I mean, they would join if it were not because of the gap closing. But if the gap closes, the two limiting projectors that you get are different. So this is why we claim that there is an interesting subclass of these mixed states which take mixtures of these two limiting states. So I think it would be interesting to use, I mean, to take this theorem and study cases as you are.
An interesting example is bipartite dimer models, which have extended critical phases. Mm-hmm. And you can also get gapped phases, but you can close the gap and have an extended critical phase. And I'm wondering, yes, that was the case I had in mind.
Thank you for the suggestion. I think that would be quite interesting to explore. Sure.
Okay, if there are no further questions, let's thank the speaker again.